In section 8.2, we're talking about chords and arcs. There are a lot of theorems in this one, so just get ready for that. Have your pencils ready. So we're going to start out by talking about some basic definitions here. So we're looking at a circle. That red segment PQ is called a chord. What is a chord? That is a segment whose endpoints are on a circle. It does not go through the center. If the endpoints are on the circle and it went through the center, that would just be our diameter. So again, segment whose endpoints are on a circle, not going through the center. PQ, so that blue kind of arc there, is an arc. An arc is really just a piece of the circumference, so part of the way around a circle, not the whole thing. And those are going to lead us to a lot of the theorems we're going to talk about today. So if I'm looking at this diagram, our first theorem we're going to talk about, if angle AOB is congruent to angle COD, then I can conclude that arc AB and arc CD are also congruent. This theorem works the other way, so if I knew that the arcs were congruent, I could then assume that the angles are congruent. All the theorems we're going to talk about today kind of are going to go back and forth too. Next theorem. Looking at a similar diagram here, but now I'm looking at some chords. If angle AOB is congruent to angle COD, then chord AB is congruent to chord CD. This one also works the other way. So if I knew that chord AB and chord CD matched up, then I would know that the angles were congruent as well. Next theorem. If chord AB is congruent to chord CD, then I can conclude that arc AB and arc CD were also congruent. So again, if these chords are congruent, then the arcs match up. Other way around, if I knew that the arcs matched up, I could assume that the chords matched up. Almost done. Next theorem we're going to talk about, within a circle or in congruent circles, chords that are equidistant from the center are congruent. So they're the same length away. So in this diagram here, if I knew that EO and OF were congruent, that would conclude to me that chord AB and chord CD were the same distance away from the center, and those would also be congruent. Also, this works the other way around as well. So if I knew the chords were congruent, I would know that EO and OF matched up. Last theorem we're going to talk about. If AB is a diameter and is perpendicular to to a chord, then we know that it cuts it in half. So in this diagram, basically any line going through the center of the circle, if it hits a chord at a perpendicular angle, then it's cutting it in half. So in this diagram, if AB I can see is perpendicular to CD, then I can conclude that CE and ED are congruent. I also could say that arc CB and arc BD are also congruent. Now, we're going to use a lot of these different theorems to solve problems here. So I'm going to show you two examples of where we would use some of these theorems to solve an algebraic equation. So I'm looking at this diagram, and I want to figure out what is the length of RS in circle O. So looking here, it looks like RS is a chord here. Let's use the information that we have. Let's look at our notes and see all of our theorems there and see what I could figure out. I'm first going to look here, and I'm marked that PQ is congruent to QR. I also would know that because OQ is going through the center of the circle and it's perpendicular, so that's another way I would know that these are congruent. Basically, I know that PQ and QR are congruent. I know that PQ is 12.5, so QR would be the same thing, also 12.5. PR is the whole segment, so it's those two segments added together. So PR is 12.5 plus 12.5, which is 25. Why I wanted to figure out what PR was is because PR and RS are equidistant from the center. So I know that PR and RS are the same measurement because they're equidistant. So if PR is 25, then RS is 25. So these are going to be kind of tricky. You're going to use the theorems. Think of it kind of like a puzzle. Use the theorems to see what you can match up to see what you can say is congruent. Let's look at one more example that might involve the Pythagorean theorem. Keys that you'll know when to use the Pythagorean theorem is if you could see a right triangle on the diagram. Again, that's always not going to indicate that you're using the Pythagorean theorem. This case, we're going to. So I want to figure out what is the radius of circle K here. So again, remember, the radius is going from the center to the outside of the circle. Given that information, I want to figure out what that is. So seeing here that Kn, again, is something going through, it's a line going through the center of the circle, and it's hitting that chord at a right angle, I know that it's cutting LM in half. So Ln would be half of the whole thing, so half of 14. Again, I know that because it's cut by a perpendicular bisector through the center of the circle, so ln is equal to 7. Why I wanted to figure that out is because I can kind of see a right triangle here. Now, I have 2 of the legs. To find that missing hypotenuse, I would use the Pythagorean theorem. So I'd set this up by doing 3 squared plus 7 squared equals r squared, and solve from there. So finally, my radius would be about, if I'm rounding to the nearest tenth, 7.6 centimeters. Again, this section can be a little bit tricky if we're not taking careful notes, so make sure you have all those theorems written down. That's going to help you a lot for our lesson that we do tomorrow.